Okay, so this one says show that the tension in the cord, which was originally 0, has increased to 3 mg as the bob passes through the lowest point. So we've got the situation where initially pendulum bob is out here, capital M, and the tension clearly is 0 there, and the tension is going to increase as it reaches its final state at the bottom, where we go to a 90-degree angle. So it's a good idea, I think, to consider the forces at the second stage. There's no point considering the forces at the first stage, because the only one is going to be the force due to gravity, which is going to be capital M G. Down the bottom we've got two forces, and they combine to produce the centripetal force. You can consider this as circular motion because it's got a length of string radius r, and there's the tension force pulling it upwards will be greater than the force due to gravity. Otherwise you can't maintain that circular motion. So there's a centripetal force required. Anyway, let's look at the FC. Centripetal force is going to be the sum of these two. The centripetal force is towards the centre, so we'll make it Ft being positive then, as well as Fc, because they're in the same direction, and you're minusing, because it's in the opposite direction, the force due to gravity. Okay, so that's looking at the situation and getting it worked out. I'm going to reread the question again and see how it works out from there. So show that the tension in the cord, which was originally 0, has increased to 3 mg as the bob passes through the lowest point. Okay, so in this situation here we're looking for Ft. We know that Fg is going to be capital M G. We know Fc equals mv squared over r, in this case capital M v squared over r. So remember, the goal we're aiming for is 3 mg. It's a show question, so we can't just substitute that in and expect it to work out. But we've got that in mind, so we're going to have to get rid of that v and that r somehow. Something else to consider then is what formulas have that v and that r in it, or something equivalent. Well, maybe energy is going to help us. That's my first thought, and that happens to be the right thought. At the bottom you've got your kinetic energy, half mv squared, so there's a v squared in there. That's perhaps what made me think of that, and the m in this case is going to be our capital M. Don't want to confuse myself with that. And at the top over here we're going to have gravitational potential energy. It's always mgh, again capital M. See, if I wasn't aware of this I might get myself a bit mixed up. mg, again appearing mg, and h. H in this case is the distance that it falls through, vertical distance, which is also the radius. So mgr is going to be a better way of expressing it. So what are we trying to find out? We know that mgr equals half mv squared. I'm going to have to go to a different colour so it's a bit clearer. But mgr is equal to half mv squared, and this has got all of our elements in fact. We've got our v squared, we've got our r, and we've got our m and g, and the half is just a nice convenient thing. So we want to rearrange and simplify for either v squared or r to substitute into this part of the equation. So I'm going to do it for v squared. Well, we could just do v squared over r, why not? So let's cancel the m's, that's going to make it easier, and rearrange this to get 2g equals v squared over r. That's correct, yep. So we can just substitute 2g in place of the v squared over r, and that's going to give us a new equation. Do it in a new colour because it's a new equation. and then 2G, which we could call 2mg, equals Ft minus mg. So that's coming from this equation, substituting this in onto that side. And we can rearrange and shift this all around a little bit. For instance, this is going to be 2mg, so 2mg plus 1mg from the right hand side here is going to equal that tension force that we're looking for, and that makes a nice 3mg, and that's exactly what we were looking for. If we go up, that was our aim. So fantastic.